thanks for having me, guys. Sounds like you guys have had a few of these talks before, but basically, kind of what I want to share with you is my story as an engineer, because I think one of the most important things that I kind of remember as being a high school student or a college student is looking forward into the future and thinking about being an engineer and what that meant. And I had no idea or how to get there. And so maybe by sharing my story and how I got there from college on and high school on, can inspire you. So, like I said, I'll talk about how I got here and also kind of some of the lessons I learned so far. So growing up, aside from loving to take apart anything and everything, I also love skating, surfing, being outside in general. So that's just a little bit about me. I grew up in Memphis, and then I moved out to San Francisco in 2007 and started a bioengineering program at Santa Clara University, which is down in Santa Clara, which some of you guys are probably familiar with. And during my junior and senior year, I started doing a few internships. The first internship I worked for was Nest. How many of you guys know Nest? Yeah, cool. So that was a really fun project. Mostly what I worked on there was actually, there's a bunch of infrared and proximity sensors in the bottom. I know some of you guys were using some ultrasound proximity sensors. Same sort of thing in the bottom of this, except using light instead of sound. And that was used to detect how many people were in a room and learning habits based off of that. So obviously the thermostat adapts to the number of people, things like that, and learns over time. So once I graduated from Santa Clara, the first company I worked for after completing my biomedical engineering degree was a company called Peak Surgical. And they made this device called the plasma blade, which sounds like an awesome thing from like a Star Wars movie or something. But basically what it was is an electroscalpel that used really concentrated RF energy to cut tissue. So the nice thing about this is normally when you cut with a scalpel, it bleeds a lot. But with this, it prevented a lot of bleeding because you're actually burning the tissue at the same time. So it's cauterizing the wound. So this was a really fun project, and it's important because the way I got this job was actually my senior design project and working with them my senior year of Santa Clara. So I'll give you, this is a quick demo of how the blade works. If you're squeamish, don't watch this because it's human tissue being cut with the blade, but I'll play this demo really quick. So normally during these surgeries, you'd see a lot of blood here as soon as they cut into it. I don't know if you guys can see this, but with this device, almost no blood. And it's a really kind of groundbreaking technology. So the places that they use this type of devices a lot is for getting your tonsils out. Because if there's a lot of bleeding when you're getting your tonsils out, it's clogging their view, they don't know what they're cutting. So with this, it's a really great way to do it much more effectively. But the problem is that when I started working with them in collaboration with my senior design project, they're like, look, the problem with these devices is that they spark a lot. And with tonsillectomies, for example, there's a lot of oxygen being delivered to your lungs and also anesthesia gases to put you under. Those are both super flammable. And so you can imagine sparks in your mouth plus flammable gases that are leaking out of your lungs, not a good combination. So here's a simulation of kind of what happens. You'll see a tube come in, and it's the oxygen flooding the space. We're simulating this chicken breast as your tonsils in your mouth. So you can see sparks, and then when you start to leak with the anesthetic gases and oxygen, you'll get a big flame in just a second here. So you don't want that. Let me pause that for a second. So what we did was, our idea was, here's a normal endotracheal tube that you would put down your throat. This cuff inflates, and that actually seals your throat off, and then they're delivering oxygen and anesthetic gases through this. And this is actually where the leak generally occurs, is that doesn't create a good seal in your throat. It's not a perfect circle. So what we said is, well, what if we could detect that leak right at the source, build a system to prevent that, and shut the machine off before any flammable gases get to where this procedure is happening in your mouth. And so you can see here, again, we'll play the rest of this video. In the next simulation, the first thing we did was, okay, well, let's build a more accurate model than just chicken breast in a tube. Let's actually build kind of a simulated mouth. And then you can see here, this is our simulated mouth now made out of clay. and then there's the endotracheal tube leaking, and so the same sort of thing is happening, right? So our solution was, like I said, to build this endotracheal tube that had sensors on it. So you can see the system using an Arduino, like I'm sure a lot of you guys are using today. We had an oxygen sensor that was measuring the oxygen levels, and then we had our warning system, so a bunch of LEDs and speakers, and then the gas delivery system. So when the oxygen concentration passed a certain threshold, we turned on the solenoid valve, which delivered a diluting gas, which was nitrogen. So the gas would mix with the oxygen and it would make the area safe again. And also the other part was that we could shut off the machine. So that was a project that I built several years ago. I can show you the final product of that, which is kind of ripped apart now, but you guys can come check it out afterwards. And here's our modified endotracheal tube with the sensing lines that would feed back into the system. I can show you how that works here. So what you'll see is, again, here's our prototype, both the device and the new endotracheal tube. And again, you can see the risk level here, and then we'll deliver gas to simulate a leak in your throat. And you can see the risk level increasing because it's detecting a higher level of oxygen that's dangerous. And then once it gets to a certain level, it says, hey, we're shutting the system off, and we're going to deliver nitrogen. So now it's delivering nitrogen, diluting the whole area, and returning to a safe level. So really, really simple project, something that any of you guys, I'm sure, could build. You know, it's just LEDs and Arduino and controlling different outputs. But what was cool is this company loved this idea, ended up patenting it, and now one of the biggest med device companies in the world, Medtronic, is using this as a patent. So, you know, just to give you an idea of things that you guys can build very simply that are also can be used in real life and solve real problems. After I worked at Peak Surgical, I worked at a company called Avenger, which is another med device company. And what they did was, or what we built there was a device that would clear your arteries from clogged cholesterol or tissue. So this was a particular device, that's the tip of the device there, called the Ocelot. And we had a laser imaging system that would scan the inside of the artery and create a cross-sectional view to see where healthy and diseased tissue was. So I can show you a little demo of how that works. So the doctors would make an incision in your leg and guide this tool up into your artery where there was a clog. And then this is what they would see on the screen outside of your body, where you can see the rings of healthy and diseased tissue. And the whole time it's augering through and creating and clearing your arteries. Kind of like a roto-loop for your veins. And I can pass around some prototypes which are actually actual devices. Don't worry, they've never been in a human body before. But so just to give you an idea, they're pretty long devices, and they get tingled really easily. But I'll hand this around in a second. Someone else to get untangled for me. There we go. So like I said, this is the end of the device that they would actually navigate into your arteries. So it's really, really tiny, obviously, because it has to fit inside your arteries. But they'd make a small incision in your leg, and they'd guide it into actually over your aortic arch into your other leg, where the blockage typically is. And then again, as you can see, cutting a path through the blockage, and then they'll deliver other treatments, either a balloon or something else to open it up. But you guys can take a look at this. The most interesting thing to look at is the tiny engineering which was a CNC machine, and then a lot of the perforation in there actually rotary laser cut into the steel. Oh, this is So I worked there for a couple of years, and then I got a call from Google X, and I had no idea what the project was going to be that I was going to work on, but I ended up there, took the job, and I had no idea what they wanted to hire me for. But it turns out they were starting a life sciences project within Google X. So you guys are familiar with Google X, I'm sure. You know, the Google Glass and Google Internet, self-driving car, all that sort of stuff. But the project I worked on, the first one I worked on was the smart contact lens. And so this was a contact lens that you would obviously put in your eye. And instead of having to prick your finger multiple times a day to check your blood sugar levels as a diabetic, this actually had an integrated sensor on it that would monitor your tear film glucose levels. So just as effective as monitoring the blood glucose, but just in your tear film. So that was a pretty cool project, and what was game-changing about that was that you could continuously monitor, rather than a few data points a day, it would be hundreds or even thousands of data points, and really changing your understanding about diabetes, or physicians' understanding about diabetes. I think I have one of those sensors, this little part here. See if I can find it, it's tiny. Yeah, here it is. So, you gotta look in there, but this whole package, so that's a sensor. It's a chemical sensor, obviously optimized for blood glucose. And then this is the microchip, which is really, really small, custom designed. And then this is a small capacitor that was a temporary storage solution instead of a battery, because it was really, really low power. And then this big gold ring here was an antenna. So it was actually passively powered. You hold up your Android phone with NFC. It would take measurements by talking to this antenna through that antenna. So you guys can check that out. Another project that I worked on there, which was super fun, was this wearable here. And it's a little bit fancier than your average Fitbit. This one actually has a bunch of sensors on it for doing non-invasive detection of small cancer cells that are circulating in your bloodstream, as well as any other sort of plaques that are circulating in your bloodstream. So this is how I ended up here, was because they were really interested in my knowledge of vessels and designing small things that go inside your arteries. So kind of drawing the line there, but I'll give you a little. This is a little.
The nanoparticles would be introduced to a patient's body via a pill which is taken orally. Once in a patient's bloodstream, they would be able to bind to cancerous cells or to a fragment of cancerous DNA. The nanoparticles can also detect fatty plaque inside blood vessels that is on the verge of breaking free and causing heart attacks or strokes. With a magnetic core, the nanoparticles would send out signals picked up by a wrist-worn sensor that would analyze them and inspect the patient's body one or more times a day.
Yeah, so that's a little bit of a description of how that worked. So I worked on that for about 2.5 years, which is great. And the team I worked on was about 5 people, and it was about 200 when I left. And I decided to leave last year to actually found a company in a totally different space, not in device related. And the company's called Flow Labs. And what we do at Flow Labs is we've built this small sensor device that attaches to your surfboard, your skis, your mountain bike, all sorts of things that you want to attach it to for outdoor activities. And we learn your habits and preferences by tracking all the metrics about your session. And then the other half is that we actually share that information in real time. It's always connected. And through that, we're kind of creating this outdoor information network, kind of like what Waze does for traffic, where everyone's crowdsourcing information about traffic. Except we're doing that for outdoor experiences. Knowing where your friends are on the mountain, how many people are out there, knowing where your friends are. Did you guys ski or surf or mountain bike? Yeah, cool. So I can show you a little demo of that, and then we can talk about maybe how you would design this device. Mine is cool, so. So here's just a visualization of all that data that we can collect. Cool. So that kind of gives you an idea of the data that we can collect and the whole experience that we're designing around the product. So now I want to ask you guys, based on our user inputs, like what kind of sensors would you want to put in this device in order to understand different motion metrics or position metrics, things like that. Yeah. Accelerometer. Yeah. You want a Twix, Butterfingers, or Kit Kat? Yeah. Kit Kat. All right. All right. So what else? Temperature probe. What would you do with that?
What the conditions outside where you are.
Yeah. Twix. Cool. All right. This is for the bonus question at the end. But what else?
GPS to know where the crowds are.
Yeah. GPS. We got GPS, accelerometer, temperature. What else? Yeah.
I mean, I put like a sensor in to see if you're about to hit someone or something. Skiing.
Yeah. How would you sense that?
I mean, if someone came up like with someone or like had like you had a sensor and they came up like right next to you skiing,
Yeah.
like beep.
So like a proximity sensor of some sort, like ultrasound or LiDAR or something. Yeah. Cool. What else? Oh, yeah.
Barometer.
Yeah. Barometer. Yeah. Absolutely. Cool. Yeah, so you guys are all absolutely right. The ones that we put in here are GPS, accelerometer, barometer, a gyroscope for understanding orientation, and then magnetometer, which gives you kind of real-world orientation. It's basically a compass in 3 dimensions. And then we also share that data over Bluetooth and 3G. 3G is how we do the real-time stuff over cellular network. So now that I've talked about where we are now and how I got here a little bit, I want to share with you just a few guiding principles that I've learned so far and have really helped me kind of in my career and both as an engineer and just, I think they're also kind of valuable things to keep in mind just in life in general. So, here's our, yeah, so the first is that simple is always better. And a great example of that is the design of this. And kind of the backstory there is good engineering isn't about showing off with how much we know by making things really complicated or designing something really complicated. It's actually almost always better to keep design simple, and it's actually kind of hard to do that. So with this, the Ocelot design, which this guy right here, one of the design constraints we had with this was, was you see this little curve at the end here? That is actually very intentional. We call it a jog. But if you can imagine, the vessels in your body are all sort of tortuous and they're all sorts of zigzaggy and going all different ways. And so for a surgeon to be able to navigate through that's pretty hard. And we came up with a lot of different solutions for how you would be able to steer this thing through a 3-dimensional space, really complex curves and things like that. Everything from having little pulley wires that aimed it in different directions and pointing in different directions to having nitinol, which is like a memory metal, to actually activate curves in different directions. But what we arrived at was that just simply setting a little curve or having this little jog in the end and then allowing the doctor to be able to steer that in different directions was the best solution. And you think, oh, that's too simple, like why don't we add some electronics or motors in the end and steer it that way? But that was really all that was needed, was that simple little jog. So simple is always better. And this is saving thousands of lives a year, or thousands of legs a year, thousands of lives. So simple is always better. This one's really important from like a consumer-facing and product perspective, which is solve real problems, but also solve them for the real world. And a good example of this is the Segway versus boostable. You guys are familiar with both? Yeah. So Segway was a really great idea. It was a great design, and it solved a problem. It helped people get from A to B more efficiently. But the problem is that it didn't fit into people's real life. It was this kind of nerdy thing, and it's still kind of viewed as this nerdy thing. Sorry if anyone owns a Segway. And the problem was that it wasn't extending any natural interactions. It wasn't fitting into people's lives that they were used to. So, on the contrary, boosted board has kind of taken off. And a big reason is that this fits into people's lives. They're much more used to something like this form factor, more so than this. With this, you're standing 12 inches above anyone else, right? Unless you're on NBA board. With this, you're still kind of at eye level with everyone, and it's also something that people are used to seeing. So it fits into real world interactions in the real world much better than this did, and that's kind of a good example of why this took off and why this didn't. The last one, or actually the second to last one, is just stay stoked and make things. Making things is so important as an engineer, and it just as a maker in general. I would say that the biggest thing that I regret about my college experience is that we only had one senior design project where I built this. I wish they had one every year, freshman, sophomore, junior year, to really push me to make things and think about the whole design process from beginning to end. And that's why I think this program is so important and it's so fantastic, and I'm so happy to be a part of it and see, you guys are so ahead of where I was. You're 4 years ahead of the first time that I made anything or thought about making anything. So kudos to you guys for already staying stoked and making. And the last one is break the rules. And I don't mean like go out and break the law or disrespect your teachers or disobey your teachers. But what I mean is don't be afraid to question the way things are and offer better solutions. So Nest, I think, is a great example of this in that your thermostat was something that's just sitting in your home, and it's been there forever. No one really thought to ever offer a better solution. They just didn't question it. It's your thermostat. That's how it works. And then Nest came along and totally reinvented what it meant to have a thermostat and what it could do. And I think that's a really good example of that. So the last thing I want to leave you is a little snippet from someone who I think is really inspirational, and whoever can tell me first who it is at the end of the video, they get the butter maker.
When you grow up, you tend to get told that the world is the way it is, and your life is just to live your life inside the world, try not to bash into the walls too much, try to have a nice family life, have fun, save a little money. That's a very limited life. Life can be much broader once you discover one simple fact, and that is everything around you that you call life was made up by people that were no smarter than you. And you can change it. You can influence it. You can build your own things that other people can use. Once you learn that, you'll never be the same again.
Yeah, so anybody know who that is? There you go, Steve Jobs. So Steve Jobs is the founder of Apple, as you may know. But I think that's so true, is that everything around you that you call life was made up by people that are no smarter than you. And I think engineering and getting your hands dirty early is the best way to really understand that, and the best way to really feel like you can influence and change the world. So keep making, keep doing great things, guys. It's awesome. That's it. Questions, comments, concerns?
To start off, how did you choose a major like theater so early? Do you feel like it doesn't seem like it did, but do you feel like your major educates you to your career later on?
Yeah, that's a good question. So I chose biomedical engineering because growing up, actually it's a pretty specific story. My dad is an engineer, structural engineer, and I always grew up making things, and from building tree houses to taking apart the PCR and stuff. So I always knew that I loved making, and when I figured out that engineering was what you call that as a professional person, and I was like, cool, I want to do that. The other half was spending a lot of time outdoors. I was really into wilderness survival when I was a kid, and my parents gave me this wilderness survival book, which had all these backwoods remedies for if you broke your leg, how to make a splint out of tree limbs, and how to suture a cut on your head with your own hair, stuff it's weird stuff. But it really got me interested in the idea of medicine and how medicine is also a form of engineering, because you're looking at what are the symptoms and solving problems through that. And so when I ended up at Santa Clara, I realized that they had a program that combined both of those things, which was making and also medicine. And so that's how I chose biomedical engineering. And I wouldn't say that bioengineering pigeonholed me by any means. In fact, I think it's a fantastic major for getting a multidisciplinary look at all the different fields of science and engineering, from chemistry and biology, which you don't get exposed to as a mechanical engineer as much, to the harder maths and the engineering side of things. So I think it actually set me up for opening a lot of doors versus pigeonholing. Anything else? Yeah. They're all super challenging in their own ways. I would say Flow Labs is challenging, my current project, because I'm just taking a step outside of just being an engineer, and I'm also building a business. So there's some really interesting challenges with that. But I would say the most technically challenging project was probably working with Avenger on this device. There's a lot of really fun mechanical engineering challenges that go into building what looks like just like a core. But this is actually like really complicated, like lots of layers, steel braiding, all sorts of mechanical engineering issues to solve. So that was probably the funnest and most challenging. Yep.
Why did you decide to switch from your old projects to the surfing, more outdoorsy?
That was really because there's a couple reasons. One is, like I said, I grew up loving the outdoors.